Okay, so today, with some luck, my goal is to tell you why we can actually get a branch, an unbounded branch for the tree in the right model. So just to recap where I left off last time, I was talking about the construction, and it is such that given a tree in our model, there is a branch in an outer model. So the next topic is how we argue that this branch actually exists in the model that we want. So let me start with just something about, your prototypical just vanilla branch lemma. So this is just a few sentences about the general way those branch lemma arguments go, just in the abstract. So usually one is in a situation where there is so you have a tree in some model V, and then you have some model, say W, a forcing extension, and you have a branch in this outer model, and you're trying to put the branch down to V, so show that V is in here. So what one does is let E, for instance, be the all nodes U such that there exists some condition P. P forces U is in the branch B, where this is W is just some forcing extension by some poset P. So now if the branch is new, what does that mean? So since you may well assume you're working below a condition forcing that B is an unbounded branch. So E, the levels of the nodes in E are unboundedly often, so they reach up to the height of the tree. And if B is new, that means that there is something called splitting among the nodes in U, i.e., so first, let me write the fact, alpha such that T alpha intersection E is non-empty. This is, well, not just unbounded. This actually equals the height of the tree, because that's what a branch is. And now if B is new, then there is splitting. So this information is decided in contradictory ways, i.e., you can always find unboundedly often nodes U in E such that this can be extended, and in this picture trees go downwards to nodes U1, U2, which are both in E but are incomparable in the tree ordering. Right? Otherwise, if this wasn't the case, then we'll just take some, U in E, and let's take every V greater than U in the tree ordering that's forced to be in the branch. Then this will create a branch. So if the branch is new, there has to be such a splitting. So the standard splitting arguments go along the lines of, okay, well, we have this splitting unboundedly often, so let's build either, like U sigma, P sigma, where sigma is taken from some index, where at each point you get this picture. So you build it, and then at the end, you take a level which is, say, the supremum of the levels in the tree of U sigma, and you have to make sure that your construction is such that this is below the height of the tree, and from there you do some pigeonhole principle using that the levels of the tree are not too big. So then finally use that T alpha is less than, well, not too big. So this is just a very broad overview of what people try to do when they try to show branch lemmas. So now in our case, let me start just kind of highlighting some of the problems. So one of our problems is we don't have the tree, we have a name for the tree. Another problem is the actual, so these branch lemmas usually work nicely when this quotient is nice, i.e. when this is closed enough, the forcing is closed enough, or you have forcing that used to be closed, followed in a extension by a chain condition model, something like that. So here, our picture is as follows. So we have, so now let's recall the picture from last time. So this is our main model, VG, where we want to show the branch exists. This is where the tree is. Now, up above, we have this VG star, where G star is generic for R star, which I defined last time. And they project to each other. So here we have V, A, script A, script I, where script A is generic for the add poset, script I is generic for the pre-cre poset. Here V, A, and in between here we have many intermediate models. So for instance, we have VGP for every P in the pre-cre generic. There is a model that sits between VG star and VG, okay, depending on. So all of these are forcing extensions where, if you remember, the forcing has the same underlying set, but the order is different by how much interaction you allow between the different coordinates. Okay. And now, both of these project, so VG star and VGP for every P in I, project to VA model QP, VA model Q, and there is a projection here, and this is the nice quotient. Okay, so this is the type of quotient for which I want to consider splittings. Okay, this quotient. Okay, and recall from last time, I'll use that at the end. The G is actually the union of the GPs over all conditions P from the pre-cre generic script I. Okay. All right, and now let me talk something about names. So let P dot be a name for the tree. So you might ask, well, a name in which model for which poset? Well, so one can define starting from, I guess here, the actual tree is in VG, of course, and it's also in each one of those VGPs. But by getting an appropriate name in for this tree in VA, one can define names T dot, where T dot is in VAQ, because now that the tree is also here, so we can take a pre-cre name for the tree.
Sorry, Dima, when you write A, V of A, you mean generic for A.
A is the
This is, yes, script A. Yes, script A is generic for math BBA. And script I is generic for math BBA. Okay, so note that this forcing extension is just by the pre-cre I. So I can first take an I name for the tree where the name is defined in VAQ. But by taking the right names, one can also do, so for any P in I, let T dot P be a name in, let me write where it is, in V a QP, again be an I name for the tree.
Do they always exist? Do they exist for every P or?
Yeah, because the tree, so for every P from the generic, for the pre-script, from I script. Yeah, for every P for I script, because the tree is in all of these models, so you can take an I name in here and you can take a name in here. And actually, if you define, so that's an exercise in names, but if you define those names from a name taken in R mod A in here, you can define them so that they always, their evaluation is always the same object given generics that project to each other. Although formally they're defined in different ground models, their evaluation is always the same. So just for simplicity of notation, I'm going to write just T dot for that name. So it's always an I name for the tree. Okay. And okay, but, well, I'm going to write this. So, and they can be, so in particular, T dots of, I will equal T dot P sub I, which is what I want to say. So in particular, when I write something like that, Q forces U less than T sub dot V over I, Q is taken from the pre-reposit I, this happens over the ground model V A Q if and only if, okay, let me write it here. So in particular, Q forces U less than T sub dot V over VA Q if and only if Q forces not A U less than T sub P V over V A QP. So from now on, for the rest of the argument, I will just write this without specifying which ground model I'm considering, because the names can be defined so that it's not ambiguous.
You require there that Q is stronger than P?
Yes, Q will be stronger than P. But in all of my arguments, Q and P will always have the same stem. So they're always compatible. You might as well assume that. Okay. All right, so now so T is an I name.
So do you first clean P's in I somehow to get
Sorry?
the stem?
Sorry?
You have plenty of P's in I.
Yes.
They may have different stems, so you restrict yourself to...
In the branch lemmas that I'll use, it'll be a branch lemma for a fixed stem, which will hold densely off and on. This is actually the next point I'm getting to. Okay, but so for now, okay, so let T is an I name for the tree. Similarly, let B be an I times Q name for the branch. Now, B is in V adds. Okay, so the branch is here from VG star to going into VA. I mean, that's a nice product forcing. So B is an I times Q name for the branch. So now what did I show? So I showed the following. So definition, let H be a stem. So I showed that there is unboundedly often stems H for which the following holds. So I'll call these daggers of H holds if we have an unbounded subset J of mu, where mu, recall, is the height of the tree, some psi less than kappa, and some sequence of conditions p alpha alpha less than mu, such that the stem of each p alpha equals h, and alpha is not less than mu, alpha is taken from J, sorry. Also, we have for every alpha less than beta, p alpha meet p beta forces that alpha psi is, let me say, u alpha is less than u beta, where u alpha denotes alpha psi. So this is just from the Tsai's paper. And alpha such that p alpha is in I, this is unbounded. And for all alpha, p alpha forces over I that u alpha is in the branch. Okay, so these are the two key parts. Well, and also
Here,
there's unbounded.
P alpha intersects in I intersects the J.
Yeah.
Here, when you're asking the set of all alpha such that P alpha is in I, unbounded, you want them from J or not?
Yeah, so for all alpha in J, yeah. Yes. Well, P alpha is defined only for alpha in J, yeah. So what Itai showed is that densely often, so for any stem, you can find an extension of that stem, call it H, for which daggers of H holds. This is what Itai showed. So daggers of H holds.
Dima, could you move up the? Could you move up the other one?
Yeah. Densely often, and by densely often I mean in the natural ordering of stems. So given any stem, one can extend that stem to something, to a stem H for which daggers of H hold. So Itai's argument happens just looking at those two models. So he considers VG star, so he shows that in VG star there is a branch, and by working in a model like this, where one can lift the embeddings, and by what I used to call lemma 1, 2, 3, and 4, you show the existence of such a unbounded J and alpha maps to P alpha. Okay. And I think I wrote this at the very end of the first time. Okay, so we have this. Now let me define the splitting that we'll be using here. Okay, so definition. So remember, I want to concentrate just on analyzing this quotient. Okay. H splitting, so let H be a stem. So suppose that H is a stem and U is a node on the tree, where node, this is just a pair of ordinals. H splitting at U holds if we have the following. is, well, you know, I want to have this picture. Let me just erase that. No, I want to have something like this, but in the right model. So I want to have this picture over a quotient like that for some p, because that's the nice quotient, this one. This is the nice quotient. If there are conditions p in I, R1 and R2 in Q, so this was, recall, the underlying set is, this is the third coordinate of all of these mutual type forcings, R star, Rp. Such that, okay, so I want PR, so the stem of P is R, means the stem of P is H, PR forces that U is in the branch over, you know, this I dot Q. PRI forces that, oh, and I need also note U1, U2, forces that UI is in the branch for I1 or 2, well, just this picture, and I want for each I in 1 to 2 PRI to be below PR with respect to, you know, this main poset. And P forces that U1 is incomparable to U2, that will be the splitting, and I mean, I want to be in this nice quotient, so that means that I want both R1 and R2 to be in the generic, so now this is script, generic Q's of P. So this means if I draw a picture, this means that we have a splitting like that over.
But U1 and U2 are extensions of U. U1 and U2 are beyond U in the tree, right?
Yes, and this follows from here. Oh yeah, of higher levels, you're right. Yeah. Level of UI is bigger than level of U, which together with this fact will give you the Dirac extensions. So if this definition looks kind of weird, what H splitting says is that there exists a picture like this. So there exists some P with stem H, so such that for some conditions R, R1, and R2, we have that PR forces U is in the branch, and then PR1 forces these guys in the branch, PR2 forces these guys in the branch, and this contradictory information is decided over this quotient, the nice quotient. So there V script A script QP is the smaller model, and V script A script Q is this model W.
We decide the levels of U and U1 and 2.
Yeah, so they are big. They don't have to be the same, but bigger than U. Yeah.
They're decided by, I mean, PR forces it or whatever.
But they are pairs of ordinals.
They're pairs of ordinals, so yeah, I can say they're alpha, psi, theta, yeah. And let me make one note. So this definition is done in VAQ, right? Because I'm saying there exists, you know, such a P, and then here I talk about the generic script QP. So I have to work in a model which knows about all of these generics. Okay, so I'm actually Well, you can either read this or there exists such a picture where all of these are forced to be in the branch by conditions where the prickly part has stem H and the contradictory information happens over this model math BBQ mod script QP. This is a picture, this is my H splitting. Stem piece H. Okay. So, well, as in the end, I want to define a branch kind of like this, taking all the possibilities, possible nodes forced to be in B above some level. So I'm going to argue that at some level, you cannot have H splittings unboundedly often. I mean, that's the main point. Well, okay, so for every H, let alphas of H be the supremum of all alpha less than mu, such that there exists a node of level alpha, so in T alpha with H splitting. Okay. And the key lemma, is that, so suppose daggers of H holds, so we are in the situation of the Itai's conclusion, then alphas of H is less than mu, being the height of the tree. So once you show that for every such H and daggers of H holds densely often there is no more H splitting, then, so how many H's are there? Well, the number of stems is strictly less than mu, because those are finite sequences of points in P kappa kappa n. So then the idea is so then what one does is takes the supremum of all those alpha H's, takes a node of level above that supremum, and then, the branch is given by just taking all the possibilities above it forced to be in the branch. And then there's no more splitting. Now, at the end of the argument, one goes back to this fact to prove that if there is a splitting between G star and G, that means that there was a splitting there was a H splitting for some H. Okay, so that's in a nutshell. Okay, so I'm going to say a little bit, of course, so this is the key lemma, but are there any questions? Yeah.
How do you handle that in the second but last line it's not written P together with R?
With this one?
Yeah, you can define what you want, but you now need to you don't have much splitting, and then from the negation you want to conclude that you have a branch. So if I negate this, then only no P forces incompatibility, but how can I then get a stronger one which forces that they are actually comparable?
This forces that they're incomparable.
No, you have the negation. You said you have from one point on you have no more H splitting, so you have the negation of all this stuff here. So I only have that the P cannot force an incompatibility, but maybe somehow one needs that in P.
Oh, actually, you don't actually negate the H splitting. What you end up having is, if the branch is new, then there is a splitting, and splitting between G star and G gives you H splitting. So you actually never negate this statement.
Okay.
But you're considering, we'll be considering at the end nodes above those alpha H's, for which there is no more. Okay, so I'm gonna, okay, so this is, let me just talk about this for now. So that's the key splitting lemma for daggers of H, alpha H is less than mu. So, okay, So the key claim, write it as a splitting lemma. Okay, so proof suppose otherwise. Okay, so I guess proof. I figured it's more friendly if I put quotation marks. So suppose otherwise. So suppose alpha h equals mu. Okay. So suppose you have for some stem h such that daggers of h holds unboundedly often, you can find this h splitting. So then we built conditions, yes, p sub sigma, r sub sigma, note u sub sigma for sigma taken from. So here the splitting argument will be in the style of Magidor-Schell as the tree property at alpha omega plus 1. So this is actually taken from kappa omega to the less than omega, and I think this is a good time to remind people of which cardinal is which. Okay, so this is kappa, then the supercompact kappa ends, there's a primum, kappa omega, mu, and then lambda is the weakly compact here, so mu is kappa omega plus, becomes kappa plus, those guys in the end become singularized. Now here we're working in VIQ, so here they're not singularized yet, but this is the height of the tree. Okay, and since the tree, so T dot is a name for a tree of levels of size less than mu in the model after you've done the pre-Cris stuff, their levels while working in the name can be assumed to be indexed by ordinals up to kappa. So build this such that, assuming splitting, such that, well, so some of the things are, if sigma prime extends sigma, we want this condition, p sigma r sigma to be less than or equal to sigma prime to be less than or equal to p sigma r sigma, less than or equal, means stronger, in just, the ordering, R star mod A ordering, I times Q. We also want for every sigma, P sigma R sigma to force that U sigma is in the branch B, again, in the product, okay? And then we want the splitting, i.e., for every okay. And then now for the whole box. Oh. For every sigma and for every, say, I less than j in kappa omega. So what is the splitting? We want, well, the notes u sigma I and u sigma j to be incompatible. So P P sigma of I meet P sigma of j forces over I that u sigma of I is incompatible to u sigma of j. And finally, I want to say what the stem of all of these is h, and that, so maybe this should have been done before 3, because this is, the meat of those conditions. So for every sigma stem of P sigma is h. Okay. So although the prerequisite itself is not countably closed, if you keep the stem the same, then in the end we can close them up. And now, so this has to be, of course, a witness of H splitting. So another part of H splitting is that the quotient, we're doing over some nice quotient. So for every sigma, R of sigma is in the generic given by script Q piece of sigma. Okay. So I'm going to draw a picture of like this, well, every case is a successor case here, I guess. So this is built by induction on the length of sigma, which is always finite. I'll never be able to get this down. Oh, okay. Oh, this like, okay. So we'll leave this part because that's actually crucial in the proof of the successor step of how this system is built. So, I mean, in order to build this, in a nutshell, you have to show that so if you're given, some condition and some note, so suppose you're given P sigma, R sigma, and U sigma, and you want to build all the P, R's, and U's of sigma up to I for I less than kappa omega, you want to show that you can get, let me call it I, so UI will, stand for sigma concatenated with I. So you want to show that there exists like a simultaneous splitting for kappa omega many nodes. So here in this picture, what we've assumed is just that you can do two splitting, okay, for H. Now, how do you get the simultaneous splitting? Well, this is when one relies on the precise statement of what was in Itsai's paper, is that in this outer model, one can build those nodes which kind of like simultaneously are witnessed to be in the branch B by some condition P alpha, such that P alpha meet P beta forces U alpha is less than U beta. So the idea is going over to the model where you have I, get kappa omega many nodes, so let me call them VI, for I less than kappa omega, such that each VI is like one of those conditions, so that trees go downwards in this picture, forced to be in the branch, and then split each one of them. And then the UIs will be appropriately picked nodes from that two splitting. So first get a sequence of nodes that are comparable and actually forced to be in a branch. Split below any two of them by our assumption that you can always do H splitting, and then show that the UIs can be picked from those splitting, and then they will be incomparable, and their incomparability will be witnessed by conditions like this, which is exactly kind of what I want here.
Don't you have to every time go to an unbounded set J?
Yes, so what you do, you end up, so you use that J is in VAQ. So J itself is actually not in the generic from the precrete. So you can actually get these conditions, P alpha and U alpha and J alpha, while working in VAQ. Okay. So we don't actually work in a generic by the precrete because we don't want to. And then from there I mean, there is more to it. You have to show that on a club subset, if there is an H splitting before you, that H splitting is witnessed by nodes before you. So I mean, it takes, and then at some point to get from these p alphas to get these ones, you do end up even needing the Prickry property to make sure that you can keep the stem the same. Because at one point there is, as Heike pointed out earlier, there is a negation of a forcing, and then that's when you use the Prickry property to strengthen your condition without strengthening the stem. So that's actually exactly what you pointed out does appear here. And I think for this, for the splitting argument, realistically and humanely, this is all I can say right now. And of course, I have the paper and the preprint, and I'm happy to talk more in detail about it. But because in the remaining time, I want to say, once you get that alpha h is less than mu, and let's wrap up the story and say how from there you can define your branch. But before I do that, is there any vague questions? Just mention that at the end. Once you build this, then you do something that appears in many fast branch lemmas. So then for every f in, so this is indexed by those guys, for every f in kappa omega omega, you build, so define p sub f and r sub f to be below p sub f restricted to n, r f restricted to n for all n. And similarly, then you strengthen this condition, again without strengthening the stem, to decide a node on a level above the levels of all the u sigmas in the branch, and then you do a pigeonhole principle. So I'm just going to write for all of you do this, and then pigeonhole principle using the fact that the number of those f's is, well, this is actually mu, but it's bigger than the levels of t alphas, and also bigger than the number of stems. There is a point in the argument at the end when you do have to extend the stem once you pick a level that's above the level of all the u sigmas, and then you have to decide nodes to be in the branch on that level. Then the stems are increased, but since there are not too many stems, there are at least two different conditions for which the stems are the same. And then we get our contradiction.
Kappa omega 2 omega u?
Yeah, this is before the Prickry. Yeah, before the Prickry. But it's still bigger than the levels and the number of stems. Yeah. Okay. Okay. So now we're in good position. Okay, to define the branch. Okay. Okay. I'm gonna do this. Maybe I'll rest. So now let alpha be the sub of alpha h's. I mean that there are less than mu many stems, so this is less than mu. Well, or even say bigger than the sub, etc. Now let u be a node of level t alpha, and f star be saying g star, or forcing that u is in the branch over, so forcing technically r star over g. Okay, so now, I mean, I'm going to take all of the nodes greater than u that are possibilities for being in the branch, and argue that since we're above alpha, there can be no more splitting. So then let D, this is what will induce the branch. Let D be the set of all nodes V such that there exists S in G. S is less than or equal to S star, well, less than or equal with respect to the R star order. And S forces V is in the branch B. So now that this D is defined in VG. And it's unbounded. It's actually exactly at the levels of nodes in this exactly at tail end, mu set minus alpha. And so we argue that the downward closure of this, that this induces a branch. So D induces a cofinal branch. No, that's
one. There in the corner is the
no, that's like for pumping.
Around the column there is the stable thing. Yeah.
Okay, so what's left to check to show that D induces a branch is that there is no incomparable nodes in D, right? That for any level alpha, the intersection T alpha contains exactly one node. Maybe I'll leave the picture. Okay, so now the proof is that otherwise there must be a splitting. So there is something like U and nodes V1 incomparable V2, but both forced to be in the branch by conditions, and all conditions forcing that R in R star mod G. And then using this, let me actually call it star. So that's a splitting in R star mod G. Right? But by star, and it takes a little bit of actually working out and extending the right conditions, but you end up showing that a splitting over R star mod G, this yields a splitting over R star mod GP for some P. And that yields an H splitting. And this gives you an H splitting for some H. For some H, and you can extend H by density, so that stars of H, daggers of H holds. And then, but we're supposed to be above alpha H, and you get your contradiction.
What would be the P? Would it be the condition that forces stability somehow?
Yeah, so what this P is, you take the conditions in R star mod G, forcing that this is in the branch. Well, you extend them so that their span is such that dagger holds. You argue that, but both of them must be in some GQ. And then when you extend the pre-Cree coordinate, you get everything to be, concentrate on some GP. And yeah, so this is, this is the end of how we get the branch. And I was planning to say a few things about what's open and what's the next part of the tree property everywhere dream. But are there any questions about this? Not yet. All right. Okay, but this concludes the proof of that theorem. So, the main thing that remains open is the next step is pushing this down to accessible cardinals. So, if, for example, and this, I think I said this in the very beginning, can we get the tree property at Aleph omega plus 1 and Aleph omega plus 2? So, right now, I mean, this is very much open.
With Aleph omega strong limit.
Yes, you're right. Or Aleph omega strong limit, yeah, otherwise you can. Okay. Right now this is still very much open. I mean, even the following is kind of annoyingly open still, which would be a stepping stone question for this. Is it consistent to get the tree property, not even the tree property, but just failure of SCH at Aleph omega plus, say, failure of weak square at Aleph omega? And that's all. And in order to have even a hope of getting the tree property, first you need to show that weak square can fail. And in order to get the tree property here, for Aleph omega strong limit, you would have to get failure of SCH. Okay? But what I am reasonably optimistic at this point that can be done, and Spencer and I are actually working on this, is to push this result to Aleph omega squared. So conjecture can get TP at Aleph omega squared plus 1 and Aleph omega squared plus 2.
A strong limit.
Well, isn't it always okay, and so for example, even this for Aleph omega squared, that can be done, so that's due to Gittig-Sharon, and with the tree property can be done also for Aleph omega squared plus 1 together with failure of SCH at Aleph omega squared. And so Spencer and I believe that one can, with work, interleave collapses in this construction.
Sorry, Dima, you wrote an omega 2 rather than omega.
Thanks. Okay, and lastly, since this was mentioned in the abstract, so when I wrote the abstract for this tutorial, I was still like in the middle of working on this. I wasn't sure if I can finish it in time. So in the abstract, I did mention something about a dichotomy theorem relating the case for trying to answer these questions for Aleph omega, and so I have to say one sentence about it. And this was joint with Spencer, we showed that given a Prikry type forcing P, say if you denote less star to be the direct extension order and less than or equal to be the full order, roughly speaking, you will get a weak square if and only if P with the direct extension order preserves what I've been calling mu. Collapses what I've been calling mu. And right now, in most natural attempts for Aleph omega, weak square is appears. But yeah, so this is, I think, it for now. Thank you.
Thank you very much. Well, we have a little time for questions.
I have got two questions.
Okay.
The first one is, in this model, do you have the reflection of stationary sets at the successor of the singular cardinal?
I haven't really thought about this, but that's a good question. So that's, well, what do you? I mean, you're working on that, so maybe you know. I'm not sure, but possibly, yeah, I think possibly.
And the second question is, why are you more optimistic about Aleph omega square plus 1 and Aleph omega square plus 2 rather than just Aleph omega plus 1?
Well, because in order to add collapses, so we're starting with these supercompact cardinals above kappa, and they reflect below kappa. So, for example, when one does the Prickry sequence through kappa, between each of those, like alpha n's, that's the Prickry sequence below kappa, is, like, vaguely speaking, a reflection of the situation above kappa. So to add, to interleave collapses without, while preserving things like chain condition, etc., you need something called guiding generics. And those guiding generics kind of force you to leave an omega gap of cardinals between any two successive Prickry points. And this omega gap is because this picture must be reflected and preserved below kappa. This is why it ends up being Aleph omega squared. Mm-hmm.
Yes?
So I suppose a clear question is also if you can get some Foreman in this context of where we end.
Okay, so yeah, so James and I talked about that yesterday, and twice over beer we convinced ourselves that it's a reasonable thing to try. That probably you could, and the way one would try doing it is if you take the Cummings-Foreman iteration, but at every step in that iteration, instead of doing what they do, which is just basically kind of mutual, do this at every step of that iteration, and then possibly you can get it.
Can I ask you another question?
Sure.
Is there something else but the tree property for which this kind of thinking can be used? But you have a lot of results about the tree property, and it seems the techniques are very, very nice and involved. I would think that there is something more that can be done.
Oh, yeah, so well, one thing to look at is, as Laura said, just reflection of stationary sets. Another thing, and this usually follows from results about the tree properties, the extent of failure of square. And I guess, in general, I mean, there are many compactness type principles. So the more general motivation is how much compactness can we get in the universe, but not only at large cardinals, but at things like the, the accessible cardinals, basically. And I mean, the tree property is just kind of a very good, really representative of all of those compactness or reflection type principles that one can look at. So how much compactness can we get in the universe will be the more broad umbrella of applications.
Okay, I think our time is up. So let's thank Dima for all the three.